appreciate I appreciate everyone being patient. Thank you so much to all of our SEAL partners and to all of our site partners. Thank you so much for joining us today. We had a great crowd on Monday, and we're thrilled to have so many of you able to join today as well. I want to start out by letting folks know that we are recording today, and we will be sending out the slides to all of you, so don't worry about trying to take furious notes and write everything down, because you will be getting the slide set. The slides also have full speaker notes, so you'll be able to go back through and read to refresh yourself on anything that I'm saying that you maybe missed the first time or need a reminder of. We're grateful to our interpreters for helping us out today. I know that my teammate Jasmine sent out the instructions late in the day yesterday for accessing the Spanish, and so hopefully everyone who would like to listen in Spanish will be able to do that. If you have any difficulties with the interpretation, please put a message in the chat. My teammate Francisco Rentas is a Spanish speaker and will be able to help troubleshoot. And I do want to remind everyone to mute your lines as well. I know I'm hearing a little bit of music from someone's phone or computer. So if everyone can mute your lines, that will help us to keep a nice, clear audio for everyone to hear easily. I think that is all of the housekeeping. Oh, I know. I was asked to remind everyone, because we are working with interpreters, if you have a question or if you're responding to someone else's question, please be sure to just give a moment in time. We want to make sure that the interpreters have a moment to translate what you've said before moving on to the next speaker. So we just want to be mindful of speaking in a nice, even pace and a nice, clear voice to make it easy for the interpreters to hear you and to help us today. So I think that is the housekeeping. My teammates, as I said, Francisco and Linda Oceso, are on the line with me to help manage the technology and to help address anything in Spanish. And we will get underway. So, starting with immunology, the miracle of the human body and all its many parts, we will be thinking about our immune system like a tree. First, it has bark on the outside, which is like your skin. It's also like the little hairs in your nose and your ears and your eyelashes. Also our mucous membranes, all of these barriers on the surface of the body that help to keep things that don't belong out. Just like the bark does on a tree. We also have the different branches. So the main branches, they have little offshoots, some fruits and leaves. So we'll go through some of these parts today to help make sure that you have a sense of how they work together. And we'll start with the innate immune system. And in particular, one of the types of cells of the innate system, the natural killers, which are abbreviated NK cells. So your innate response is the body's first line of defense, starting with your skin. And as things perhaps get past the skin and get inside the body, They are the responses that happen first, right away. Um, Unfortunately, they're not necessarily able to prevent an infection because the types of cells of the innate immune system only get turned on after an infection has happened. They recognize that invader that gets inside. So if something makes it past our outer defenses, like our skin and our eyelashes, for example, those internal cells only get turned on after an infection has happened, and the natural killers are an example of that. What's interesting about the innate response is that it needs to be turned on first to enable the rest of the immune responses to follow. So the innate response is kind of like turning on the light switch, and then everything else can happen after that. The power comes on. The parts of the innate response do not have any sort of memory. So they don't remember whether you had a cold last year or flu 2 winters ago. They only see it as a new response happening right now. And as a result, we're not sure that the innate response can necessarily benefit from a vaccine. It's possible that a vaccine won't have much effect on these innate responses. But again, because we want the innate responses to start first, that will still be an important step. Just as a little point of interest, your natural killer cells work by causing an infected cell to burst, kind of like putting a pin or a dart into a water balloon. It causes it to pop and explode. So the next branch that we'll move to is our adaptive immune system, and then we'll get into some of its subparts, some of its smaller branches. So when you think about the adaptive response, this is another way of saying acquired, the immune responses that we learn over our lifetime. These are the responses that are specific to every single different kind of thing we might ever see in our lifetime. The cold, the flu, the chickenpox, the measles, and so on and so on. All of the different kinds of germs that we might come in contact with over our lifetime. So interesting is that this response takes a couple of days to really come into full effect. So you could think about the last time you had a cold or the flu, and you remember that you might have felt just awful for the first couple of days. And somewhere around day 3 or day 4, you start to feel better. That's your adaptive response that's starting to kick in and starting to clear that infection out of your body. One of the great things about this adaptive response is that we continue to develop it through our entire lifetime. We're always acquiring information about new kinds of germs that we might be exposed to. So this is where it's especially important to have vaccines that could potentially help to give us some sort of long-term or even lifelong protection, possibly. So the first of the smaller branches of the adaptive response is our humoral response. And that's the scientific name for what most of us have heard described as our antibodies. So as this little graphic shows on the right, our antibodies are shaped like the letter Y. They have 2 arms at the top and a foot at the bottom. And they are developed in our B cells, which are one of the specialized cells of the immune system. Just as I said, this adaptive response takes a couple of days to get going. Antibodies can even take longer, usually about 2 weeks, to be fully in effect. And antibodies can work in 3 ways. On the next several slides, I'll go through each of these in a little more detail, but just to give you an idea, antibodies can help to neutralize and stop the virus. They can help to eliminate the virus and clear it out of the body through a process called opsonization. And they can help to sensitize the immune system to help call all of the different parts of the immune response into action. Antibodies, different from the NK cells, our antibodies are able to prevent an infection. So they recognize that germ when it first enters the body and it's just kind of floating around, even before it has caused an infection of our cells. The antibodies can recognize it and block it to prevent an infection. And they do have memory, so they will remember that cold or flu or chickenpox that you had previously. Antibodies work as this little diagram on the right is showing. They bind down to the outside of the virus, and they're able to cover up the parts of the virus that would normally be used to attach onto our cells to cause an infection. And this is true for all different kinds of viruses and germs, not just SARS-CoV-2 as I've shown in the example, but they work the same way for all the different kinds of invaders. So this little animation will play and it'll keep repeating as I talk, so don't worry if you think you missed it, you'll get to see it again. The first way that antibodies can prevent an infection is through the idea of neutralization. So this is you down at the bottom in yellow. This is one of your cells. You're the host. And all of our cells have these different kinds of receptors on the surface. You can show them here. They look like little purple, kind of a cup shape. And ordinarily, the virus would come along and it would use some part of the proteins on its surface to attach onto those receptors. And that's how it would cause an infection of our cells, through that binding on at the receptors. So as you can see, our antibodies use their little arms at the top, and they attach to those proteins on the surface and block them. They cover them up so that the proteins are not able to attach to the receptor to cause an infection. You can think about this as if you were to put a piece of material over the top of a lock, and then the key would not be able to fit into the lock because there's a barrier in the way. Let that animation play to the end here. Okay. The second way an antibody can work is by helping to clear that germ that it attached to out of your body. So you're not going to just have little free-floating viruses with antibodies stuck to them roaming around in your body. The antibody is actually going to help clear them out and get rid of them. And they do this by using their little foot, right? So we've got the arms at the top of the antibody attached to the virus. And now they're going to use their foot to pull that virus into other kinds of specialized cells called phagocytes. And phagocytes are like your body's garbage disposal. They use their special chemical properties, the lysosome properties, to break down that virus and bust it up into little bits. And now your body is able to shed it like waste. So it clears that virus out of the body altogether. And you can see the phagocytes have their own type of special receptor on the surface that the antibody can attach to, and it pulls the virus inside that special cell. The cell uses its chemical properties to break down the virus, and now we can destroy it and clear it out of the body so that it won't be present. You can kind of think about this like putting some butter or jelly on a piece of toast. And when that antibody is all by itself, just kind of floating around, it's kind of boring. It's sort of like a piece of plain white bread. Doesn't have a whole lot of flavor, doesn't look so interesting. But once that antibody attaches to it, it's like you put some jam or some honey on your toast, and now it looks more tasty. So now that phagocyte is interested, and it's going to come along, and these other specialized cells are going to want to eat that virus up. And then the third way that an antibody can work is to sensitize the immune system and call the other kinds of cells into action. So I told you a minute ago about the natural killer cells. And it turns out that if they see an antibody attached to a virus, they can be a more effective killer. So I like to think about this, thinking about old gangster movies. And anybody who ever watched a gangster movie knows that every good hitman needs a lookout, right? So the antibody being attached onto that virus is acting as the lookout. And it's literally kind of going, yoo-hoo, pay attention, I'm over here. And calling those other kinds of killer cells into action. So in this way, the natural killer can be a more effective hitman, and it can do a better job of clearing out the virus. And the scientific name for this, because everything in science has to have a long, complicated name that then uses initials just to make it even more confusing. So the fancy name for this is antibody-dependent cellular cytotoxicity, or ADCC. So again, the idea of having the antibody to be able to make other cells more effective in their killing functions. So as a quick response of the humoral system, this is our antibodies, which attach to the virus and cover up the places that they would ordinarily use to attach to our cells. The antibodies are able to neutralize, and they work alone to block a virus from entering our cells, but they also can bind on, and just by the fact that they bound onto the virus, they can call the other parts of the immune system into action to be more killers and be better at helping to destroy the virus. So let's pause for a minute there and see if anyone has questions on this first part of the immune response. Everybody's doing okay? I don't see anything coming up in the chat. Okay. Oh, can I please assign Jasmine as a host? Yes, I will do that. I first have to find Jasmine in my little... Jasmine, can you turn your camera on for a minute so you'll pop up to the top of my screen and I can find you easily? Let's see, that's not working. So let me see if I can scroll through. Forgive me for a moment, folks. I need to find... Oh, there she is. All right, Jasmine, I have now turned hosting on over to you. All righty, continuing on then. So the next piece of our adaptive response is our cellular response. And there are two main types of cells that are involved in this part of the response. And again, because it's science, they have long names and they have abbreviations. So these two main types of cells are called our helper T lymphocytes, or you may have heard of helper T cells. That's also abbreviated as CD4 positive. And then the cytotoxic T lymphocytes, or cytotoxic T cells, also abbreviated CTL or CD8 positive. Like our antibodies, this part of our adaptive immune response does have memory, so it will remember those things that you've seen before. But like the natural killer cells, they're only turned on after an infection happens. So they have a little bit in common with the antibodies and a little bit in common with the natural killer cells. So if you're like me, a picture helps you remember better. So I think of our CD4 helper cells like the person with the megaphone who can shout, you know, hey, you guys, over here, there looks like there's something to pay attention to over here. And they can call all of those other parts of the immune system into action, and especially the killers. And the killers are like Jaws, that great white shark whose only job is to kill. So we've got our helpers and our killers as these main types of cells. So how does this adaptive response work? Well, the job of our T cells is to be our surveillance system. They're our security camera. They're like the guy on the wall. If any of you are fans of Game of Thrones, they're the watchman on the wall, always on the lookout and surveilling the body to see if things look the way they're supposed to. Do they look normal? Do they look infected? Do they look abnormal? Are they the wrong shape in some way? And the T cell's job then is to go on duty to destroy any of those cells that look infected or abnormal and clear them out of the body. And just like the natural killer cells, the CD8 killer cells are also more effective when that antibody is attached. So they also benefit from having the lookout of the antibody. And when it's the CD8s involved, you'll see this called antibody-dependent cell-mediated viral inhibition. It's quite a mouthful, ADCVI. Sometimes I have also seen this abbreviated as ADCP, antibody-dependent cell-mediated phagocytosis. So talking more specifically about that phagocyte, the garbage disposal kind of cell that's doing the work. So they mean the same thing. If it uses the P for phagocytosis, it's just a little more specific. So as a quick summary, our cellular response uses these two main types of cells, the cytotoxic cells and the helper cells. They don't prevent infection, but they do get activated once an infection has happened. They're able to help clear out an established infection. They do have memory, just like the antibodies. And as a result, we think that they can be trained by a vaccine. And we'll be talking more about how that works coming up. So let me pause again there and see if anyone has questions. So far, so good. I don't see anything in the chat. All right, I'll press on. So now we're going to turn to vaccines and how do vaccines build on this immune response. So most of us probably think about vaccines as things that we use in children. They've been around for several decades, more than 5 decades. And what we forget is that adults get vaccinated all the time. And if any of you have had a flu shot in the past, you're a perfect example. Adults also often get vaccines if they're traveling internationally. You might need to get a yellow fever shot to visit some countries. Many adults get vaccines for hepatitis A and hepatitis B, and so on. So We get vaccines in adults all the time. One of the things that we see um, as a common occurrence is that we've lost some of the vocabulary in our society. And we forget that when we talk about getting a shot, that's actually the same thing as getting vaccinated or getting immunized. The immunizations are shots. Some of this vocabulary is less familiar. And we have to remind people that they all mean the same thing. We're talking about the same action. We know that vaccines are very safe when they're manufactured and used correctly. We have a lot of experience with doing that. We also know that vaccines are very cost effective when compared to treatment. Anything that you can give in just a couple of doses is going to be a less expensive option that you might have to get for a long period of time or might require hospitalization. In the case of HIV, we know that people have to take several medications every day for the rest of their lives, for example. So anything that we can give in just a small number of doses is going to be more cost effective. Even something like the flu, where we need to get a vaccine every year, it's still cheaper to do that than it is to treat people who can become very severely ill with the flu. Vaccines have helped us to eliminate smallpox. It's now cleared out. There is no more smallpox in the world. And we're really close with polio. Last year, the World Health Organization announced that 2 of the 3 wild types of polio had been eliminated. There's just 1 remaining type in the region around Afghanistan and Pakistan, where there's been a lot of war and civil unrest. And so, public health campaigns to get people vaccinated have not been the most pressing issue. But we're getting really close to eliminating polio as well. Most recently, we've seen the success of the human papilloma virus, or HPV, which is against, human papilloma virus is one of the causes of cervical cancer in girls and young women. It's also a cause associated with genital warts and some rectal cancers in boys and young men. And the HPV vaccine gives us a great example of why enrolling a diverse cohort makes a difference. Because when they first tested this vaccine, they were only thinking of it as a way to prevent cervical cancer in girls and young women. And so they ran their studies and only enrolled girls and young women. But lo and behold, their vaccine turned out to be really super duper effective. It's over 99% effective at blocking HPV. And so then they had to take a step back and say, well, gosh, HPV is a sexually transmitted infection, and most girls get it from having sex with a boy. So we need to figure out if it works for boys and young men as well. And they literally had to start over and enroll a whole new set of trials in boys and young men to be able to prove that it was effective for them as well. So it's a good reminder of just how important it is to enroll people of a diverse cohort in our studies. We have a lot of data that helps us remember just how effective vaccines are. So this is looking at some of the most common vaccines that people get. And you can see just how effective we are at reducing the number of new infections. And a number of these vaccines are over 95, over 98, over 99% effective. At the low end is pertussis, which you may know by the name whooping cough. That's still better than 92% effective. So Haemophilus influenza type B that's listed there is one of the causes of meningitis. So we know just how effective vaccines can be when they're used and rolled out to the population. So this is a good reminder of why we are paying so much attention to having a vaccine against SARS-CoV-2. And we think that a vaccine against SARS-CoV-2 could work in a couple of ways. They could work to benefit the individual, the person who actually gets the vaccine, by helping to prevent an infection from developing into a severe illness. We want to try to keep people out of the hospital and keep them off of ventilators. And if we're lucky, we might be able to actually prevent infection altogether. And then there can also be benefits to the wider community. So if we have individuals that are not getting sick, that means that they're going to be less likely to transmit that infection to other people, which results in a healthier community. And it also benefits our healthcare systems. So, you know, as we're hearing about in the news now, we hear about, you know, the hospitals being very crowded. We're running out of ICU beds. We're running out of ventilators. So if we can keep our individuals and our communities healthier, we're going to have less stress on our healthcare systems, so that people who have all different kinds of health issues that might require an ICU or a ventilator will still have access to those kinds of services instead of them being monopolized by COVID. So let's look a little bit at how vaccines are developed. What's the process? So first we need somebody to have a bright idea of how to make a vaccine. What do they think is a technology that could work? And then typically they take that technology and they bring it into the lab and they test it out using samples in a test tube or a petri dish. They then could advance to testing it in animals. Some of the common animal models are in mice, in rabbits, and then sometimes we get into non-human primates. This picture at the bottom here is a rhesus macaque, which is one of the common primates used in HIV vaccine development, as one example. And then ultimately, you have to take everything that you've seen in these early stages and make a decision about whether it seems safe to advance onto human studies. And do we test it in people? And even when we test it in people, we work in a stepwise kind of slow progress. And ordinarily, for other illnesses before we got to COVID, the way that those stages played out was phase 1 studies that last for about a year to a year and a half, where we enroll a small group, usually less than 100 people. They're typically people who are very healthy, that don't have any other kinds of health conditions. And we're looking primarily at the safety of the vaccine. Are there side effects? Do people tolerate those side effects pretty well? You know, if you have a headache, does it go away quickly? If your arm is sore, does it go away within a day or two? That kind of thing. If the results in phase 1 look promising, then you can advance to phase 2, and that's where we start enrolling hundreds of people. Again, they're typically people who are in pretty good health, and we're going to now look at not only the safety, but also the immune responses. Are they making antibodies? Are they making T cells? Does the body seem to be reacting to the vaccine in the ways that we hope that it will? And again, if that all looks promising, you can then advance into phase 3. And that's where we start to enroll thousands of people. Typically, these are people who might be at some sort of increased risk for that illness. And it's the first time we ask the research question, does this vaccine actually work to protect people and prevent new infections, or protect people from getting a more severe illness if infection does happen? So that's kind of the ordinary, all the vaccines that we've known about before the year 2020. That's how it's worked generally. With COVID, we're doing things a little bit differently. With COVID, we are overlapping the process a bit. So instead of moving in steps where we finish phase 1 and then we go on to phase 2, and we finish phase 2 and then we go on to phase 3, in COVID, we're overlapping the steps and trying to speed the process up a bit so that we can try to, because the time is really important. We have people dying every day all around us, all over the world. And we need to find a vaccine as quickly as we're able to. So the phases of study are still taking the same amount of time. The phase 1 trial still goes on for a year to a year and a half. The phase 2 trial still goes on for about 2 years. What's different is that as soon as we get the signal of safety and that the data seems to suggest that it looks okay, we're continuing to follow those people and do the long-term follow-up, but we're moving ahead with the next phase overlapping. So for example, the Moderna company, which was the first of the COVID vaccines to get underway, they started their phase 1 trial in March. They got their safety signal and they opened their phase 2 trial in May, even as they're continuing to follow those phase 1 participants for safety. The phase 3 study opened at the end of July. Again, they're still following those early stage volunteers. We haven't given up on them in any way. So we're still monitoring them. We're still looking at long-term effects, but we're trying to overlap and be a little more expedited. The other big difference in COVID is that we have the investment of some of the government agencies that are tasked with protecting public health. So groups like the National Institutes of Health, there's also an agency called BARDA, which is the Biomedical Advanced Research and Development Authority. BARDA gets involved whenever there are these large threats to public health. So for example, when we had Ebola several years ago, when Zika broke out several years ago, that's when BARDA gets involved. So with the investment of these federal programs and the billions of dollars that they have put into it, what that has meant is that the companies don't have to spend time raising money from their stockholders and other financial sources. So if they're not spending time on fundraising, that means that they can devote all of their time to the vaccine development. And we can save a great deal of time that way as well. So this is really important. I want to really stress this slide because one of the things that we're hearing so often, and I'm sure that all of you have heard it as well, if not from your own friends and family, then from people in the news media and reports, people are worried that somehow we're rushing and we're compromising safety. That somehow if we're doing this so quickly, safety must be suffering. And what we really want to reassure people is that all of the same safety protections are in place. There is nothing that's being skipped. There's nothing that's being, we're not cutting any corners anywhere. We're just doing these studies in kind of overlapping fashion instead of one after the other. And because of the government investment, we're able to have the money to really get to work quicker and produce the doses and speed it up through the financial side as well. So who are we enrolling in these studies? A minute ago, I gave the example that the HPV vaccine has given us a lesson in the importance of diversity. And in COVID, that's certainly important as well. We know that in COVID, there are some communities that have been harder hit than others. So for example, we know that our elders, people 65 and up, have been more impacted. We know that people who have different kinds of underlying health conditions have been more impacted and have had more severe illness. people that have a greater risk of exposure at their job from doing some sort of essential work task. And often that overlaps with people from racial and ethnic minority groups. So they are the folks that have so far been hardest hit in this pandemic. So for our studies, we want to pay particular attention to making sure that these hardest hit groups are represented in the participants in our studies. Because if we want to be sure that a vaccine works for those hardest hit and most impacted groups, we need them to be involved in the studies to help us answer the question and ensure that a vaccine is going to work for them. We also need to be mindful that in order to evaluate the efficacy of a vaccine, well, unfortunately, the way that we do that is by waiting to see if people get infected. And that sounds really cold and really callous. Obviously, we're doing this research because we care about prevention. We want to keep people healthy. But if it was as simple as everybody following the directions and staying at home and wearing a mask and keeping physically distant and washing their hands, all of those good public health messages that we've been hearing, if it was that easy, we wouldn't have a pandemic and we wouldn't have people dying as a result. So we know that not everybody's following the directions. And unfortunately, that means that there are going to be people who become infected. And what our studies are designed to do is to monitor how many infections are happening. And when we get to certain thresholds, that's where we can look at the data and see if we're seeing any signs of effect. So, you know, when we think about being able to do that in a way that's timely, that's going to get us the answer as soon as possible, it's important to enroll the communities that are at the highest risk, because that's where infections are happening. So you'll see in many of the study materials that we're showing pictures of Black and African American families, people who are of Latinx heritage, older adults. These are the people, Native Americans and American Indians and other indigenous communities. These are the people that we're using as the photographs in a lot of our materials to help call attention to the fact that we want to make them a priority and make sure that we're enrolling them so that we'll have good answers about whether the vaccine works for them. So we do that by enrolling studies where we give some people the study vaccine and some people the placebo. The placebo in these trials is sterile salt water that does not contain any of the vaccine ingredients. This is the same kind of saline solution that is sterile that people might use for their contact lenses, or if they need to, if any of you are athletes and run marathons, you know that sometimes people need to be hydrated. That's the same kind of sterile saline solution. The number of people in the different groups can vary a little bit across the studies. Some of the trials are doing half and half, 50% getting the vaccine, 50% getting the placebo. And some of the studies are doing 2/3, 1/3. But either way, we've got groups to compare and help us understand whether the vaccine is protective. I just saw a couple of questions pop up in the chat. Let me pause for a minute and just look at them real quick. From RJ, yes. So I see usually data from the prior phase would be used to inform the development of the next phase. And so how are we doing that if the phases are being overlapped? It's a fabulous question. I'll use the Moderna study as an example. When Moderna opened their study in March, they had 3 different groups by 3 different doses. So there was kind of a low, middle, and high dose. And they were looking at the safety and the side effects that people had to the different doses. And so when they made the decision to move ahead to phase 2, they actually moved ahead with the middle dose because they saw that that was having the best safety profile, that the side effects were not especially severe, that they were people were able to tolerate that well. So you're correct that the results of the early stage inform the next stage. And if we design the studies well, we are still able to do that, even when we're overlapping. That's a great question. Let's see, Jennifer asked another question about funding. Thank you, Jennifer. You made a clarification and I perhaps maybe gave the wrong impression. The investment that is happening is working in a couple of ways. So part of the investment is just giving the vaccine companies the money to develop the product. A second part of the investment is to actually purchase doses of the vaccine and start to stockpile vaccine doses so that when we find out the results of these phase 3 trials, if we find out that it works, we will already have doses ready to go that can start to be rolled out to the public. And on the flip side of the coin, if it turns out that the phase 3 results are not good, if it's a bust, then they'll just destroy those doses and waste them because we would know that they don't work. So that is a second part of how the financial investment is enabling us to speed up the process. Thank you, Jennifer, for that clarification. I appreciate that. Oops, sorry, skipped. Here we go. So how do we decide whether you get the vaccine or whether you get the placebo? Who makes the decision about which of the groups that you are enrolled in? And the answer is that it's completely random. A computer decides. And the pharmacist working in the pharmacy will enter that person into this randomization system and get the answer of which syringe they should prepare. And the doctors and nurses that are in the clinic will never know what's in that syringe. In fact, in some cases, if there's the possibility that the vaccine and the placebo might have a different visual appearance, they even go so far as to wrap the syringe in a colored sleeve to disguise so that you can't tell what's in the syringe. And that helps to keep it absolutely blinded. The people in the clinic will not know what they're giving, and the person who's getting the shot will not know what they're getting. So you can think of this like flipping a coin or rolling dice. It's a random outcome. And because it's random, we talk about this as being blinded. If both the researcher and the volunteer are in the dark, then we call it double-blinded. Sometimes you might hear the expression observer-blinded, because there might be people, for example, in the pharmacy or somebody who is doing a double check to make sure that the correct syringe was prepared. Those folks may know what's going on, but the people who are involved in seeing the participant and observing the participant, they're not going to know. So you might hear both terms. But again, the idea here is to make sure that everything is kept fair. We don't want anybody to be treated differently. We don't want anybody to get any sort of favoritism. We don't want and we don't want anyone to do anything different, right? We need to know if it's the vaccine that's what's making a change, and not whether somebody changed their behavior because they thought, that they knew they were getting the vaccine and they were going to be protected, so they quit wearing a mask, for example, right? We want everybody to be doing all the same things. The staff in the clinic are going to keep counseling you about all the good public health steps to follow, because we want to be sure that it's really the vaccine that's making the difference. I see Marina made a comment that can be scary for the volunteer, and I think you're correct, Marina. That is definitely a risk that people have to really get comfortable with. And that's part of what we talk about in a consent process, to make sure that people understand that we don't know. And we don't want them to assume that they're getting the vaccine. You know, even though it sounds like a big study, right? 30,000 people perhaps are getting enrolled into a trial. That means 15,000 people are getting the placebo perhaps, or 10,000 people are getting the placebo. So we need people to really you know, assume that we don't know if the vaccine works, and they have to continue to protect themselves. So how does this actually play out? We're going to enroll a group of people. They do not have COVID-19 at the time that they join a trial. And we think in most of these studies, there's some sort of a criteria that they have some sort of a risk factor, either a risk for infection or a risk for having more severe illness. And we're going to give one group the vaccine, and we're going to counsel them about hand washing and wearing a mask and so forth. And we're going to give the other group the placebo, and we're going to give them the exact same counseling. And then we're going to continue to follow them over time. So in these studies, they're about 2 years long. People come into the clinic for somewhere between about 7 or 10 visits over the 2-year period. In between, they're checking in with the clinic by phone. They may be filling out a little diary using an app on their phone to track their symptoms, and there's any side effects they might have and how long the side effects last. So we're continuing to watch people really carefully throughout that whole time. We're reminding people to be aware of any symptoms that could be a sign of having COVID illness, and what to do if they experience any of those symptoms. And we give them all of the directions for that. And then when we get to the end of the study, we're comparing the responses. So we're going to use the blood samples that we collected at their different clinic visits, and we're going to look to see what's happening in that blood sample. What's the immune response? Do they have antibodies? Do they have T cells? If we use that blood sample in the test tube and we spike it with some SARS-CoV-2, do we see, you know, under a microscope that it looks like the blood is able to neutralize the virus? So we can do that through the results of the study. And I see Pamela confirmed, yes, there's the studies are all a little bit different, but it's approximately 7 to 10 visits in the clinic over a 2-year period. So what is this vaccine actually doing? How is it actually working? So what a vaccine does is teach our body how to recognize this invading germ, this virus, this invader. I love this particular picture because it seems to work in all of the different cultures around the world. We recognize these guys with the swords as the bad guys that are invading. Nobody wants them. We wish they would go away. And that is what the vaccine is teaching us how to recognize. And as our body learns how to recognize it, and in this case, I'm using our new coronavirus as the example. Our body will recognize the coronavirus. It sounds the alarm, right? Those helper T cells sound the alarm and call all the other kinds of cells in our immune system into action. And all of those different cells that we just talked about, the T cells, the natural killer cells, the phagocytes, and so on, all of those fighter cells and our antibodies get called into action, just like a fireman gets called to the scene of a fire. And obviously the goal is to put out the fire, right? We want to make sure that we block that infection if we can, or we clear the infection out if it has already happened, so that we can control it and keep people healthy, keeping people from getting very sick. So what does that look like? So these are actually photographs from the Vaccine Research Center at the National Institute of Allergy and Infectious Disease. This is where Dr. Fauci is working. And they shared with us these pictures that are magnified many times. What does it look like under a microscope? So on the left in purple, you see that coronavirus, and it has its big spike here in the center. We know the coronavirus has those spikes and all sticking out all over. And what we're looking for is for antibodies to come along. You can see them in purple and green. They've got their 2 arms and a tail, 2 arms and a tail. And those antibodies are going to come along and attach on that spike. And over here on the right, here's us. We're the host, remember, a cell in the human body that has a receptor on it. And ordinarily that spike protein would come along and would attach to that receptor. But what we can see is that because the antibodies have come in and attached on that spike, they're blocking the virus from being able to bind onto the receptor. And so hopefully we're going to be successful in neutralizing and preventing infections from even being able to happen. So how have we done this in the past? Some people are not seeing the slides advance. Uh-oh. I have absolutely no idea how to fix that.
Yeah, I'm not sure because some of us are seeing it. So if you are not seeing it, may you express what you are experiencing? We're not clear because, yeah.
It might just be a help to drop off for a minute and log back in. Perhaps there's something with the internet connection or the particular line that you're on. I don't want you to worry if you're not seeing the slides because we are going to send these out. You will be able to go back and see them. So even if you miss some slides, don't worry. You'll be able to hear it or see it again later, and it'll still be valuable for you to listen. I'm sorry, Linda, were you going to say something else?
No, thank you for addressing that.
Sure. Thank you for calling it to my attention. Okay, so in the past, and particularly when we think back to the polio vaccine in the 1950s, there were 2 main ways of making vaccines. And these 2 traditional approaches are called live attenuated and whole virus inactivated. I want to just, before I even explain what that means, I want you to know that we are not using these in the COVID vaccine studies. Oh, good. Thank you, Susan. You logged off and back in, and now it's working. Great. In the Operation Warp Speed studies that we're doing for a COVID vaccine, we're using newer technologies. So I just want to put that out there right off the bat. But just so that you understand how they worked, these older technologies, a live attenuated vaccine means that we weaken and weaken and weaken and weaken and weaken and weaken the virus until it's really just kind of a shadow of its former self. The idea is to do enough weakening that it will no longer cause an infection. But it will show somebody a real virus that, so that they see what that virus looks like. The second idea, the whole virus inactivated, is using that real piece of real virion of SARS-CoV-2, but they're doing some extra step to inactivate it. And usually that's something like heat or radiation or chemicals. You can kind of think of this like pickling something, right? We're making it inactive. Sometimes it's a combination of techniques that are used to do the inactivating. And these were how the Salk and Sabin polio vaccines were made. But what we saw, there was one really famous example in the 1960s, known as the Cutter incident, where the Cutter company didn't weaken or inactivate the virus enough. And so people who got polio vaccine actually did get infected with polio. And that was sort of a profound lesson for the healthcare field. And it has made us more aware of that being a potential problem. It also, funny enough, seems to be the one thing that people remember learning about, like in junior high or high school biology class. And so one of the most common questions that we hear is, well, I thought, you know, the vaccine has to have a real piece of the germ in it for it to work. And we hear a lot of people asking about whether they're going to be exposed to the real virus if they join a study. So this is important. This is why I wanted to spend time explaining these older traditional approaches, even though it's not what we're doing now, because you'll hear this a lot. People seem to know that these are the older ways of making vaccines. So in modern times, we have a whole bunch of new technologies. And it's not important that you know the names of what these technologies are. You don't have to worry about learning how each of them work. That's really not the important message of this slide. The important message here is that we don't need those old technologies because we've got lots of new options that can work more safely. And these new options don't need to use the whole virus, as I've crossed out at the upper left, and they don't need to use any kind of live or weakened virus, as I've crossed out at the upper right. These newer technologies can use pieces of the virus as a way that they've copied and made laboratory-made copies instead. So just as a point of reference, we did add in the different company names to show you which kinds of technologies the different companies are using. So Moderna, I've mentioned them a couple times down at the bottom. They are using an mRNA technology, and we'll be talking more about these individually in a minute. AstraZeneca and Janssen are using viral vectors. And then over on the right, Novavax and Sanofi are using proteins. So we'll get into more depth about each of those in a minute. So no need for the old technology because new technology gives us lots of choices and safer choices. So why do we think they're safer? Because they're not using the whole virus, number one, and they're not using the real virus, number two. They're only using parts. And in this case, the 5 Operation Warp Speed vaccines are only using the spike protein that we've shown here in the bottom center. And you can kind of think of that like maybe thinking about the parts of a bicycle. And if you only had a wheel with spokes and a handlebars and a chain, could you actually ride that bike? No, because those are just 3 parts. They're not actually functional. They don't actually have all of the working parts of the bicycle that would allow you to ride that bike. And in the same way, if we only have these little bits that have been copied from the virus in the lab, they're not the real thing. I like to think of it, it's like having a photocopy, not the original, right? It might look the same, but it doesn't have all of the properties of the original. It doesn't have all the working parts. The other metaphor that I think people can relate to is the idea that if you had an eyelash and a tooth and a fingernail, could you make a working human being? No, because an eyelash and a tooth and a fingernail don't have the ability to make copies of themselves and then also make copies of all the other parts of a human being and assemble them in a way to have a working human being. And in the same way, if all we've got is these little bits of protein that have been copied from the virus, we don't have all the rest of the working virus that would result in an infection. Layla just asked a question in the chat about side effects. Hang on, we're going to get to that. We're going there. Hold that thought, if you would please. So what are we hoping to learn from these studies? We really have 3 main research questions that we're getting into. The first is about protection. Does the vaccine actually help people create an immune response that's going to protect them against getting infected, or can it help protect them from developing more severe COVID-19 illness if they do get an infection? And you can think of this kind of similar to what we hear about with the flu shot every year. You may have heard that, you know, a flu shot might only be, let's say, I think last year we saw that it was about 60 or 65% effective. So people might still get a flu infection, but it won't be as severe. They won't need hospitalization. They'll recover more quickly. They won't have such severe side effects. So that's what we're talking when we say, you know, can we prevent people from getting moderate to severe COVID-19? They might still get an infection, but can we keep it a less severe infection? We want to continue to look at safety and monitor the side effects and any kind of reactions that people might have. And we want to continue to keep an eye on how well people tolerate those side effects. Do they go away pretty quickly? Do you need to take off work for a day because you don't feel well and you need to stay in bed? You know, do you have to take some aspirin or some Tylenol because you have a headache or a fever? We're looking at all of those kinds of reactions. So Layla, this is kind of your question. How come some volunteers become sick and show symptoms? So just because we jabbed your muscle with a needle means that you're going to have some side effects, even if you got the placebo. A colleague of mine in South Africa says, you know, that needle being jabbed in your arm, you have insulted the body. And when someone gets insulted, they react, right? We just took a sharp, pointy object and poked you. And so people are going to have a reaction. And sometimes it's just something simple, like you have your arm is sore for a day or two, or you have some redness at the spot on your arm where the needle went in. Some people have a more, different kinds of side effects. And that can be things like running a low fever. It can be things like having a headache, having some aches and pains in your joints and your muscles. For most people, these are the common kinds of side effects that are associated with all of the different licensed vaccines that people get. The same kind of side effects we see with every vaccine. And typically they go away within just a couple of days. And what we've been seeing in the early stages of the COVID studies up until now, that continues to be true. Excuse me. The people that have been in the phase 1 and phase 2 trials so far are just seeing these minor kinds of side effects. People rate them as mild to moderate. We have not had severe side effects that we've seen in the early stages. And people report that they typically go away within a day or two. Of course, the other possibility, as I mentioned, is that people might still be able to get infected with SARS-CoV-2, and they might develop the symptoms of COVID infection. So what we're hoping, again, we're going to be monitoring people throughout the study to see if they have any COVID symptoms, and to hopefully help keep those, hopefully the vaccine will help to keep those symptoms more mild. So again, we want to think about, how are we keeping people safe, right? We're not using this whole virus shown in the picture here. We're just using those spike proteins from the surface. And the name for that is the antigen. Those spike proteins are the little bit from the virus that's going to teach our body how to recognize what this virus looks like. And the antigen is the piece of the vaccine that triggers the immune system and causes it to start to respond. And again, a reminder that these are not real proteins from a real living virus. These are laboratory-made copies, so like a photocopy of the protein. So they're not able to cause illness. They're not able to cause infection. And again, we mentioned earlier that we think a vaccine could work in several different ways. And so the first couple ways relate back to what I spoke about earlier with immunology, right? If someone had terrific antibodies, maybe we would be able to prevent the infection altogether. If somebody had really great T cells and natural killer cells, maybe we would be able to prevent disease because we would be able to clear out those infected cells and a person would be able to recover quickly. Maybe if we only had kind of a so-so T cell and natural killer cell response, we would be able to slow it down and prevent the disease from getting so severe. Maybe it wouldn't advance so rapidly. You know, some of what we hear about in the news is people who, you know, they seem to be fine one day and within hours they had to go to the hospital and they had to get ventilated. This seems to be a virus that works very quickly. So maybe if we even had just a moderate kind of T cell response, we could slow it down and give people, you know, give the healthcare team more time to intervene. We also talked about the fact that a community could benefit and that there might be benefits for the people around the person who is sick, who actually, or excuse me, the person around, I said it backwards, the person around those who get the shot. And this isn't the idea of herd immunity, which has been getting discussed a lot in the media these days. This is actually a lesson that we've learned from cattle. So it really did come from the herd, which is why it has that name. And the idea, as the picture shows here, on the left, we've been able to vaccinate 95% of the cows. So those 2 remaining cows are protected because the cows around them are not able to transmit disease. They've been protected by the vaccine. On the right, you can see how different the picture looks when only 70% of the cows are vaccinated, right? So there's a lot more of those red cows that are left unprotected, but we hope that there's still going to be some protection from the individuals that get vaccine. So why does this matter and why are we hearing it talked about in the news right now? What we're hearing about in the news right now is this idea of we don't need to worry about wearing a mask, we don't need to worry about distancing and staying home. We should just let everybody get infected because then we'll have antibodies that are protective and we'll achieve our herd immunity that way. Well, I have to say that's a really stupid idea. There's absolutely nothing that is a good idea in that thought. When we have people that are dying at more than 1,000 people every day, and we have, you know, think about how angry many of us feel that there's been more than 220,000 deaths just in the United States, let alone the thousands of deaths in all the other countries of the world. You know, that's really unacceptable to think that we would just encourage people to go out and get sick because that's how we're going to protect the public. None of us want to see our family members and, you know, our loved ones, the people who are special to us. Nobody wants to see those people get sick. Nobody wants to see those kinds of deaths. And when we're having those kinds of deaths now, think about how much worse it would be if we just told everybody to, you know, ignore public health. You can do whatever you want and you'll be fine. Because what we have not seen so far is that we don't have any evidence that our antibodies protect us. And in fact, some people who've been sick get infected again, a second time. So we don't know how long any kind of protection might last that we have naturally. That's very different from having a highly effective vaccine that we can roll out to a large percentage of the population so that they're protected. And then having the people in their social networks around them benefit from herd immunity that way, right? These are 2 very different pictures. So I want folks to keep that in mind the next time you hear some politician speaking off the top of their head in a very uninformed manner. Regardless of party, I'm not trying to make a political statement. It's just these people need to learn to stick to their own lane and let the scientists do the public health messaging. So that was a lot of information. Before we get into looking at the particulars of the upcoming studies, let's pause and see if there's other questions coming up. How are we doing? Are folks following along okay? Is this any questions coming up? You're welcome to take yourself off mute and ask out loud or put it in the chat, however you're more comfortable. You're welcome to put it in Spanish as well, and our interpreters and my teammates who are Spanish speakers will help interpret for me if needed.
May I ask a question?
Please. Hi, Jennifer.
Among the studies that we've seen thus far, which side effects have been most common?
Yeah, it's actually been all of these really common ones. So having a sore arm, having a low temperature, having a headache, some muscle aches and pains, all those really common things. And again, the studies are all still blinded, so we don't know if people got the vaccine or the placebo yet. So what we know then is that people could have those kinds of side effects regardless, whether they get the vaccine or the placebo. Those are the kinds of really common effects that we're seeing.
When the trial is over, this is Goldberg. When the trial is over, will the people who participated and once it's unblinded, will the participants who receive the placebo be some of the first people who will get the?
Fabulous question. So about access to a vaccine that's found to work. Fabulous question. Yes. So there's a bit of nuance to this. It's not a real clear sort of, one way or the other answer. What we have seen so far is that the companies have said that yes, if their vaccine is shown to be effective, and if it is licensed for some group of people, the placebo recipients who are in that group of people would be offered the vaccine. And so I'm talking about that in a kind of a funny way. We don't know whether the vaccine will get approved for everybody. We hope that that's the case, but we could see that there's some sort of differential difference. Maybe we see that it works better in older adults, which would be like the pneumonia vaccine or the shingles vaccine. Maybe we would see that it works, better for one gender than another, right? We have to wait and see what the outcome is going to be. But if you are a member of the placebo group that is the vaccine has been approved for, then yes, the companies are saying that would happen. Where it gets a little tricky is what happens if it's one of the other vaccines in a different trial that gets approved. So if you're in study number A, but it's study C that winds up being effective, what does that mean? And we don't have a clear answer yet. What we think it will be possible for people to be able to get that other vaccine. So far, there's no evidence that one vaccine prevents another, because again, each one is for a different, unique, it's circumstance. So we think that it's going to be fine, but we want to sort of help people understand that there's still a little bit of uncertainty there. For as one example, in the study that's being done by Janssen, we know that they're telling people to wait a month before they get a flu shot after they get their study vaccine. So we might see a circumstance where people need to allow a little bit of time to go by before they can get another vaccine. That's another scenario that we might see. So thank you for that question. It's really important. And part of what we have to help people understand is to sort of have some patience that will, as these studies unfold, we'll be learning more about this and getting more answers, and we'll know more over time.
Thank you. Thank you for the great presentation. It was wonderful.
Oh, good. I'm glad. So let's see. I see Marina asked a question, and thank you for the translation. As health promoters, how can we convince people to get the vaccine without pressure? We know there's places where they're already pushing. Yeah, that is very true, right? we have to keep reminding people that there is no such thing in the United States as any vaccine where you're absolutely required to get vaccinated. There is always an element of personal choice involved here. Where we do see some more strict vaccine requirements, I'll use an example from here in Washington State where I live, for example, where we've had some really strong measles outbreaks in the past couple of years. And so some of the counties where they have had a real problem with measles have said that if you are not willing to vaccinate your child, you cannot send your child to public school. So the choice is still with you as the parent. You can vaccinate your child and send them to public school, or you can choose not to vaccinate, but then you have to school them in some other way, whether that's homeschool or private tutors, what have you. So there's still an element of personal choice, but we have to remember that there are consequences for other people when someone chooses not to vaccinate. One of the things that I neglected to mention when we were talking about herd immunity, there are always going to be people who are unable to be vaccinated. And so, for example, thinking about somebody who's too young, we've got little babies that might be too young to get a vaccine. We've got people who might be getting chemotherapy and have some sort of compromised immune system as a result of other illnesses, where getting a vaccine might be more than they can tolerate. So there are always going to be people who have, some sort of exclusion for health reasons. And there are certainly people that have religious reasons or philosophical reasons where they object to the idea of vaccination. I'm thinking of people, for example, in the Mormon faith or the Church of Latter-day Saints. So, these are all different kinds of scenes where people have perfectly valid reasons for not wanting to be vaccinated. And we need to just remind folks that choice still does rest with the individual. But what we hope is that they'll be open to learning about it and learning about what a vaccine can do and learning about how a vaccine works, so that if they're not sure, maybe they'll be willing to get some education and then at least be able to make a more informed decision. So that instead of just sort of having that gut reaction of, you can't tell me what to do, right? They'll actually be making a decision that's based on some good science, some good facts, whether they get that information from us, from their doctor, from a public health agency, right? There's lots of good, reliable sources for information. And we want to help people learn about it so they can make a more informed decision. And what the consequences are of that decision, right? That if you're not vaccinated, that actually means something for other people as well. Let me look back through the questions here. Layla is asking, I'm wondering about using antibodies. Okay, Layla's question is about using antibodies for people who have recovered or to help them recover rather than a vaccine. Fabulous question, because the answer is that's possible also. We just heard about this with the president, actually, that the president, when he had COVID-19, received some of these experimental antibodies. The CoVPN is involved in those studies as well. We have a set of teammates that are based in North Carolina that are leading the monoclonal antibody studies. That's a whole area of research as well. The idea is that instead of giving you a vaccine and teaching your body how to make the antibodies directly, we skip that step and we give you the antibodies right off the bat in an IV fluid. And so that's another area of research that's being explored. Those studies are happening right now as well. And if you visit the CoVPN website on the science page, there's more information about how antibodies work and the studies that are happening as well. So I'll encourage you to take a look there. Let's see, Marina had a question which has been graciously translated. If someone becomes seriously ill who's responsible for their care or even their death? Yeah, brilliant question. So this is something that the consent form will tell you more about when you're learning about a particular study. Each company might handle this a little bit differently, and the consent form is where you will learn the details of how it's being handled in that particular trial. So in general, if there are side effects related to getting the vaccine, you know, if, for example, if you had some sort of, I'll use an example, an infection that was about maybe the syringe, maybe they forgot to wipe your arm with alcohol, and so it wasn't sterile, and you got an infection on your arm from where the needle went in. That, you know, that sort of side effect that's caused by the procedures is being covered. Actual COVID illness is not a covered side effect in these studies, and people are given more information about why that is and how does that work. So I'll encourage you, I know that each of the SEAL partners is matched up with a research site in your area that's actually enrolling volunteers and doing the study. I want to encourage you to talk with your partner clinic and have a look at the informed consent form and talk about that with your research partners and understand how is that being handled in the specific study that's enrolling in your community, so that you'll have a good, clear answer that's specific to your location. Let's see, Marina had a second question. When they get the vaccine, can they spread it to another person? No. So if someone actually gets COVID illness, then yes, that they can spread to another person. If a person is making antibodies and T cells in response to the vaccine, T cells we don't transmit to others. Antibodies can be passed from a person who is pregnant to their baby while the baby is still in the womb. So antibodies can be transmitted from mother to child, but the other parts of the immune response we don't transmit to other adults around us. So that's a really good question too, clarifying those immune responses. Great, these are wonderful questions, everybody. Thank you, very thoughtful. All right, so now let's press on and look a little more closely at these 5 studies that we're doing under Operation Warp Speed through the CoVPN. So first I want to share a timeline. So we had the Moderna study that opened at the end of July, and just last week, Thursday, 1 week ago today, they fully enrolled that study. They had a little over 30,000 actually. It was, I believe, 30,328, if I'm not mistaken, was the total. So those individuals are now all making their way through the study. They'll be followed for 2 years. They are getting their shots in the trial and being followed. AstraZeneca and Janssen have both opened. They have been on a safety pause, and I'll talk more about what that means in just a minute when we get to them individually. So their enrollment is just getting started, and the pauses were just lifted. So the enrollment is going to be starting up again, probably within the next week. Novavax is coming up in November, and Sanofi is coming up in December. And I want to just be cautious, these November and December dates are projections. They might vary a little bit. It might not actually be the 5th of November or the 7th of December. Those are just target dates. So we'll see when they actually open. Everything has to line up just so. So how can we think about these vaccines, and how are they alike and how are they different? We talked briefly about the antigen that they're using, the spike protein So one way that we like to talk about vaccines is that it's kind of like making a sandwich. And cultures all around the world and countries all around the world all have our different variations on a sandwich. You know, in Vietnam, they call it a banh mi. And in France, they maybe use a baguette, whereas in San Francisco, they maybe use their local sourdough. But people all over the world have sandwiches. And so we found it a useful way to think about talking about how a vaccine is made. And we can do that by thinking about the different parts of a sandwich. So maybe you're not a very good cook and you don't know how to make a sandwich. So you actually need the recipe. You need somebody to tell you how to make the ingredients. So some of the vaccines in that way use just the genetic code for the spike protein. They're not using the actual protein, the actual ingredients. They're using the recipe to teach you how to make the ingredient. So we'll see some examples of that coming up for vaccines that use the genetic code. Then we've got vaccines that use some sort of a vector or carrier. You can think of this as how do we get the ingredients from the plate to your mouth? We need some kind of carrier to wrap them up in. And that can be lots of different things. It can be a different virus. It could be a virus from a human. It could be a different virus from an animal. And you can think of that like using different kinds of bread. Is it whole wheat? Is it sourdough? Is it rye? And so on. We've heard already that our vaccines are using the spike protein as the antigen. So that's the meat in our sandwich. And for the sake of discussion, we'll say that all of the vaccines are making turkey sandwiches. They're all using the same filling. But we know that for other diseases, for example, if any of you have seen any of the HIV vaccine studies, we've had lots of different kinds of techniques being used. And so, you know, you could think of it as a turkey sandwich, a ham sandwich, a peanut butter and jelly, an egg salad, a tuna fish, right? There's lots of different kinds of filling that could go in a sandwich. And so for some diseases, there's lots of different choices about what to put in into the vaccine. For COVID, so far, it looks like we're sticking to the spike protein. And then what happens if you make your sandwich and you think, gosh, this is kind of boring, sort of bland, doesn't have a lot of flavor. It could really use something to kind of boost it and, you know, give it that little bit of, you know, extra kick, little something, something to jazz it up. And that's the idea of using an adjuvant, which you can think of like condiments that you put on your sandwich. Maybe you use a little spicy mustard, a little ketchup, a little horseradish, some hot sauce, garlic aioli, anything that you would do to give a little more oomph, right? And that's exactly what an adjuvant does. It helps your body have a stronger reaction to the vaccine. And so we'll see in the next few slides about two of the different adjuvants that some of the companies are using. So we'll go one at a time and look at each of these. Oh, actually here, before I go into that, I just saw a question from Layla. What do we think about the different vaccines from other countries? Layla, I have to be honest and say that I have not seen a lot of the science about any of those being reported. I think it's fabulous that other countries are doing their own studies and that they're bringing additional products into research. I think that's terrific. I don't know very much about what the processes are in other countries. So my assumption is that if we actually learn that a vaccine is licensed in another country, that it will still have to be submitted to the US regulatory bodies to be approved to roll out to people in the US. And I trust that we have good systems that will review what that data shows from the other countries and make a decision about whether they think it's appropriate to bring that vaccine into the US as well. I've seen some media stories about Russia doing, you know, that they've approved a vaccine that only got as far as phase 2. That gives me a little bit of concern. That sounds a little sketchy to me. But I also think that if Russia were to apply to the FDA, I don't think the FDA would approve a vaccine that had only completed phase 2, because we have tougher standards than that. So I think I probably would take a little bit of a wait and see approach, and make sure that you know, the different kinds of scientific groups that review and evaluate the data, you know, that they would do their job, and they would tell us whether it was appropriate for that vaccine developed elsewhere to be given in the US. I know that many of these countries, for example, South Korea has a very rich biotech environment. They have a lot of pharma companies there. China, the same. There, you know, this is a big area of the economy in Southeast Asia, for example. So, and I know that they are, you know, they make a lot of the medicines that people take and a lot of the generic drugs that we use all the time. So I think that there's the possibility that that could happen, but I'm gonna watch for what is the, you know, what does the FDA think, and do they approve it for use in the US? It's a great question. So let's turn our attention now to the studies happening here in the US. We mentioned that Moderna was the first one to open. They are using the branding, they call their study the CoV study, short for COVID. Their vaccine has a complicated name that just kind of looks like alphabet soup, mRNA 1273. And as we mentioned, this is using the technology called an mRNA vaccine. And we can think of this like the recipe. I'll say more about that on the next slide. The study opened at the end of July, and it just finished enrolling last week, so a little bit under 3 months to enroll 30,328 people. There are 99 clinics across the United States that are involved in doing this, and they are now following those volunteers for 2 years. So as we mentioned, this idea of mRNA means that we're using the genetic code, the recipe for how to make the spike protein. So instead of actually using copies of the spike protein in the vaccine directly, this vaccine uses a bit of the genetic code, or you can think of this like the instructions for the cells. And once the vaccine liquid gets into our cells, it teaches our human cells how to make that spike protein and to put it out on the surface so that the other parts of the immune system can see it. They're called antigen presenting cells. And the antigen presenting cells will take that genetic code and they'll manufacture that spike protein and push it out onto their surface. And now everything else is the same as what we've been talking about, right? The rest of the immune system will see that spike protein and react to it and hopefully make antibodies and T cells to fight it off. The difference is really about, instead of using the ingredients directly, it's teaching your body to make the ingredients using the recipe, which is the genetic code. So then we come to the AstraZeneca study that opened in August. You might also hear people talking about the vaccine study happening at Oxford University in England. These are related. The Oxford scientists have entered into partnership with AstraZeneca, so they're using the same vaccine. You hear it talked about as the Oxford product. You might also hear about it called ChAdOx, which is how that funny abbreviation is pronounced. That study opened in end of August, and it is planning to enroll 30,000 people as well. I mentioned that it has been, well, actually, let me save that for a minute. The AstraZeneca study is using a carrier, a vector, and the vector that they have chosen is a common cold virus called adenovirus that impacts chimpanzees. So it's an animal virus, not a human virus. And Adenoviruses are one of the things that cause the common cold and upper respiratory infections. Because they've chosen a chimpanzee version, our body definitely recognizes it as something foreign that doesn't belong. It doesn't look human. And so our immune system tends to have a very strong reaction. We've seen this happen in vaccines for other diseases as well. The sandwich filling, again, the antigen that they're using is our spike protein again. And so in that way, it's similar to the other companies. Now, I mentioned that there has been a safety pause. So there was one case in England, one of the people enrolled at Oxford, that had a more severe safety reaction. And that what we saw was that the studies all around the world were put on pause. So AstraZeneca had the study going on in England. There was also one in Brazil and one in Africa. Excuse me, in South Africa specifically. They paused all of the global studies, and we want to make sure to help people understand that that's a good thing. It kind of sounds scary because one person had a severe side effect, and that makes us think that, well, maybe more people could have a severe side effect. So we want to be careful and help people understand that when we're talking about, tens of thousands of people enrolling, and we noticed that one person had a problem, and we stopped the study as a result, what we want people to understand is that that's a really good thing. We're paying really careful attention. And if there's something severe that happens, we stop the trial until we can explore that and figure out what happened. Now, none of us know whether that person who had the severe reaction got the vaccine or got the placebo. We have no idea, because that's confidential information. We don't talk about other people's health conditions, right? So we don't know all the details of that individual's health. We don't know whether they got the vaccine or the placebo because the study is still blind. But what we do know is that an independent data and safety monitoring board reviewed all of the data. And at first that happened in England, and the equivalent kind of group, I don't know if it has the same name in England as it does in the US. The group in England decided that it was safe to continue, and so they opened the study at Oxford back up. In the United States, our safety monitoring board said, you know what, we want to see not just the information about this particular one case, we want to see all your data from any of the studies that you've done for any disease that are using this chimpanzee adenovirus. So in the US, we took an even more cautious approach, and we looked at a lot more information. And just in the past week, they have decided that it is safe to proceed, that they will lift the pause. So the next thing that happens is that we go back and we update the consent form, because now we actually have some new information about a person who had a more severe result, and some investigation into that result that happened. And so we changed the consent form to make sure that people have more detailed information. So for the people that are already enrolled in the trial, they'll go back and they will re-consent them. They will use that updated consent form, and they'll ask them to update to go back through it with the people that they already enrolled, make sure that they have the complete full set of information, and people will be given the choice. Do you want to continue in the study, or would you prefer to drop out now that you have this additional information? And people will sign the consent form again if they wish to continue. For anybody now that is enrolling for the first time, they will be enrolled using this updated consent form where they get the complete story of what we know. So I want to emphasize to folks that we should think about this as being a good thing, right? We're being really cautious. We're being transparent with people and sharing the information that we know. And we know that we have the symptoms that are able to work and pick up on, if there's just one severe response, that's enough to shut down studies in multiple countries and put them on pause for more than a month while these investigations took place. So people should feel good that their safety is really being looked out for, and we take it very seriously. In the Janssen study, they have given their trial the name the Ensemble study because, like an ensemble, we all have to work together to make research happen. Their vaccine also has a name that just looks like a bunch of letters and numbers, ad26.cov2.s. And their study opened about a month ago. They are doing a bit larger study because they wanted to involve a larger group of countries. So they are using the funding through Operation Warp Speed to pay for the 30,000 participants in the United States. And they're using their own money to fund the additional countries and additional 30,000 volunteers that will be enrolled elsewhere. So we've got a larger presence in South America and Central America. And then we also have Ukraine in Europe and Philippines in Asia and South Africa on the African continent. So a bigger global look at how this vaccine works. And they're following a pretty similar science as AstraZeneca is. They're also using a vector. They chose a human adenovirus called adenovirus type 26, or AD26 for short. So you could think of this, it's still a turkey sandwich, right? It's still using that spike protein, but they're using whole wheat bread instead of sourdough, right? They just changed their carrier, but the insides of the sandwich are the same. And so they have also been on a safety pause for the past few weeks. We haven't yet heard, they did a better job of controlling the leaks to the media. So we don't know really what kind of a serious event this was yet. We don't know if the person was getting the vaccine or getting the placebo. Same kind of process, right? There's been this independent review where they've looked into the details of this individual's health. Was it related to the vaccine? Was it not? And just last week, they made their decision that it is safe to continue and that enrollment will reopen. And just like AstraZeneca, they are now working to update their consent form and get that approved by the regulators. And in the same way, they're going to now go back with their participants, reconsent any of the folks that had already enrolled, and same process there. Novavax is the next one coming up in November. Their vaccine, it's a little tricky because the name looks very similar to the name of the virus. It's just got this RS tacked on to the end. So we have to always be careful whether we're talking about the virus or whether we're talking about the vaccine. And that RS stands for recombinant spike. So meaning that they took the spike protein and they've changed it a little bit. They've tinkered with its genetic code a little bit and combined the genetic code in a slightly different way. They also use a technology called a nanoparticle. And nanoparticles are a type of just a little teeny tiny little protein that they can attach these spike protein copies onto to help carry it into the body. But again, in the same idea, you know, our body recognizes that it's foreign and mounts a response. So they expect to be starting their enrollment next month, and they're going to be enrolling in the United States and Mexico, 30,000 volunteers. Novavax is also using this adjuvant called Matrix M. And as a reminder, we said, you know, the adjuvants are like adding a little condiment to your sandwich, some hot sauce, some spicy mustard, some horseradish. So Matrix M is actually derived from a plant in nature, and it's that is used in a lot of different kinds of medicines. And they're hoping that this Matrix M adjuvant is going to help people have a more stronger response to the vaccine. So you can think of this different from, oh, you know what? I think I forgot to mention this in, no, sorry, I'm getting ahead of myself. So we'll think of this, for the sake of our sandwich metaphor, this is like a little ketchup. We've made it red in the picture here. So Matrix M is our red adjuvant added to our turkey, which is our spike proteins. But because there's no carrier, right, we don't have any kind of bread in this sandwich. We just kind of have the ingredients on the plate. And you know, so if it were food, you would have to use your fingers to pick it up, right? But it's still, you know, the same kind of idea of the sandwich still applies, right? We still have the filling, the spike protein, and we still have the condiments for some extra power. And here's where I was getting ahead of myself. The 5th study is from Sanofi Pasteur, and they expect to open their study in December. They also have, you know, all of these scientific names are, you know, they don't just roll off the tongue. They just seem like these random letters and numbers combined. So CoV2 pre-SDTM is the awful name of their product. And this is also a subunit protein vaccine that's using just that spike protein. They are expecting to get underway in December. They're waiting for the data to come from their phase 1 and phase 2 studies. And they expect to enroll about 35,000 people. They are also expecting to do an international trial that'll have countries in Asia, Africa, Europe, Latin America, and the US. So they're still working on the process of selecting their sites. We don't know for sure yet where they're going to be. So stay tuned. We'll be hearing more about that. I apologize. I don't know if it picks up. There is a lawnmower going outside my house, and I hope it's not too distracting or too much noise. I'm sorry.
We can't hear it, Gail.
Oh, excellent. Okay, I'll try to ignore it myself then. Okay, so Sanofi, just like Novavax, they're doing a protein vaccine. So there's no vector, no carrier, and they're not using the nanoparticle either. So there's no plate. It's just some turkey, and they're also using an adjuvant. So they're using a different adjuvant. Theirs is called AS03, which is, we've seen AS03 get used in vaccines for other diseases as well. We've done some studies of it with HIV vaccines in particular. So again, not quite a whole sandwich this time, just some ingredients, but they're using the antigen and the adjuvant in their vaccine. So if we wanted to try to stack these up side by side, we can think about these different variables, right? We've got to sort out all of these different pieces in our studies. So we need to decide which technology are they going to use to make their vaccine. So Moderna is using the messenger RNA. AstraZeneca and Janssen are using virus vectors. One is using chimpanzee vector, one is using human vector. Novavax is using this nanoparticle. Sanofi is using just the bare protein. You have to think about whether they want to use an adjuvant. They need to think about the dose, how much vaccine actually goes into the syringe. And then the timing, do they get 1 dose? Do they get 2 doses? How much time between doses? And they have to think about the route. Where are we going to give this vaccine? Now, I hadn't mentioned that so far, but in all 5 of these studies, they're giving the shot in the deltoid muscle of your arm, which is up here at the top, just below your shoulder. It's a big muscle which is an advantage. It means it can absorb the liquid and spread it around to lots of cells. But in other diseases, sometimes, you might get a vaccine in the muscles in your thigh or in your behind, right? So every vaccine has to make these decisions about where should the vaccine be administered. And if you're a person who likes to see them in a table form instead, you can kind of look at them side by side this way. We see our 5 different designs. We see that 2 of the products are using an adjuvant. We can see that the doses are a little bit different. So that says something about, the ingredients are not necessarily all equal. They may not be as strong on their own. They may need to be used in larger quantities in order to be effective. You can think about that, even for how you use common medicines today, right? If you have a headache, you might take 2 Tylenol, but if you're having severe arthritis pain, you might take 4 Tylenol, or Advil maybe is a better example. So the doses are a little bit different. If you have not seen this symbol that kind of looks like the letter U with a tail on it, that's the symbol for micrograms. So you might be familiar with grams and milligrams. Micrograms are 100 times smaller. And then the idea of VP is viral particles, which is another way to measure the amount of vaccine that's going into the dose. All of these studies are giving a shot in the arm, and you can see that 4 of the studies are giving 2 shots, either 3 or 4 weeks apart. One study, Janssen, is testing a 1-dose regimen, so theirs is a little bit different. We've been hearing rumors that we may see a second study from them using a 2-dose regimen. So that's potentially something we'll see more about in the future. We don't know for sure yet. So we'll see what's coming. I also want to note we put a little star on the dose in the Sanofi trial because they're still waiting for the results from their phase 1 and 2 studies about which dose should move forward. Someone asked about that earlier, right? What do we learn from the early trials to inform the next phase, right? So they are, in their early trials, they're looking at 2 different doses. So we don't know yet which dose will advance into their phase 3 study in December. So we'll stay tuned for more information. The other question that we hear from people is, do we think it would be a good idea to have more than one effective vaccine? And we want to say absolutely positively, yes, that would be great. The first reason is we want to give people more options, right? We said earlier, we don't know for sure whether a vaccine will be approved to use for everyone or whether it might only be approved to use for some group of people, perhaps by age, perhaps by gender, we don't know. So having more than one vaccine that works will increase the odds of having vaccines that are going to serve all different kinds of people. We also know that there's just this practical question of if we want to have enough doses of vaccine to be able to give it to the billions of people across the planet, we don't have one company that has the manufacturing ability to do that by themselves. So if we have more than one effective vaccine, that shares that manufacturing burden across several companies, and we'll do a better job of getting enough doses made quicker to get out to all the people that need them. Again, we don't know yet if one of these scientific technologies is going to work better than another. Is a nanoparticle better than a chimpanzee vector? We don't know. So having multiple studies and giving really looking at all the different scientific options can help us really make sure that we're not leaving some good idea in the dust, right? That we're really looking at all the choices. And if it turns out, maybe they'll work differently, we don't know. Maybe one will be harder to manufacture than the other, and so we'll have more doses available of one type, but it'll take longer to make the other type. All of these things are possibilities. So what's been really interesting is that we have been seeing this effort to really involve global manufacturing capacity, really trying to work together and collaborate for shared solutions. And what's clear is that, you know, we're collaborating in ways that we've never seen before. This is really, you know, unprecedented in our lifetimes. So it's nice to see the kinds of collaborations that have been getting off the ground already. So again, that was a lot of information. Let me scroll back. I see that there's several things in the chat. Let me scroll back up and look to see what we've got here.
And Kat Dancing is the one. You answered Layla's question about different vaccines from other countries. Kat is asking, what is another example of a vaccine that works the way Moderna works?
Thank you so much. So this mRNA technology is new. It has not yet been used in a vaccine that's licensed, but it has been tested in studies that have been all the way through the phase 3 and that are in the process of applying for licensure. So we know that it has shown the ability to work. It just hasn't gotten far enough along yet to actually roll it out to the public. So this potentially will be another possibility where we hope it works and could be rolled out to the public. So the mRNA technology is new. The other company, I didn't mention the company Pfizer, because they are not part of Operation Warp Speed. They are funding their study themselves. Pfizer is also using this mRNA idea in their vaccine, so in their study. So we could hear either from Moderna or Pfizer about mRNA vaccines. So yes, it is the antigen presenting cells from the Gallup site that asked this. They are the ones that take that genetic code and are able to turn it into a bit of protein that they push out and display on the surface of the cell so that the rest of the immune system can see it. The T cells then react to it, right? So the antigen presenting cell is showing you the spike protein so that the T cells can react to the protein. Maggie did a little bit of internet searching while we've been online. Thank you, Maggie. And so there's several products underway in China, and they are running their trial in several other countries on other continents as well. Good to know. Thanks, Maggie, for the helpful tip. Layla wants to know more about this is really important. Layla, I'm so glad you asked this. This is a really important safety question that you've raised. Will people know which vaccine they're getting and whether they have a choice of vaccines? So what we've been really careful to do in the CoVPN is that any one clinic is only doing one vaccine trial at a time. So at a particular clinic, there will only be one study offered. But in a city that's large, and I'll use some of our areas like Los Angeles, New York, Atlanta, there are others as well. Those are just the first 3 that popped into my head. There may be more than one clinic in that city because it's a big metropolitan area. And so in some cities, it is indeed possible that different clinics will be offering different studies. So different vaccines. What we're working to be careful of, and why I say that this is a question about safety, is that we want to make sure that any one person only enrolls in one trial, and that we don't run into a situation where somebody thinks, well, if getting one vaccine is good, getting 2 vaccines must be better, so I'll enroll in 2 trials. And in fact, that's not smart, because these vaccines are not proven yet, and we don't know yet all of the safety, and we don't know yet whether they work, and we also don't know yet how they might interact with each other. So in the same way that we have to be careful about taking medications that might have an interaction. We need to be careful about vaccines. And in particular, the reason that that's so important in a research study is because we have to be able to answer the question, does this vaccine work? And if we have somebody who also gets the second vaccine, well, now you've complicated the mix, right? You've introduced another variable that we weren't prepared to answer. So we want to be sure that we're not messing up the science and resulting in a problem where we're not able to get a clear answer. But we also want to really be careful about the safety of that volunteer and keep them from being in a harmful situation. So the sites work really hard to kind of query people and sort out, you know, are you sure you haven't joined another trial? You haven't gotten any sort of, you know, other treatments for COVID and that sort of thing. We're trying to be really, really careful that they're only enrolling in a single research study with the possibility of getting one product. Super important. Thank you, Layla. Let's see. Jennifer, looks like Jennifer added a follow-up comment. Thank you, Layla. This is a great follow-up as well. The consent form is going to tell you which product, which study you're enrolling in and which product. And it's also going to explain the blinding that the researcher won't know and you won't know either. And so, you know, if you think you have aches and pains or a fever or a headache or any other kind of side effect, the research team is going to, you know, they're going to treat it just the same no matter who is reporting that symptom, because we don't assume that you're having a side effect just because of getting the vaccine. People who get the placebo can have side effects as well. Layla, thank you for sharing that helpful comment back to Jennifer. I appreciate that. Let's see. Arti, I'm not sure if I'm pronouncing your name properly. I apologize if I got it wrong. Arti is asking, what about someone who gets dose 1 but is able to get dose 2 for some reason? So once you're in a study, you don't give up any of your rights. If something that came up prevented you from getting that second dose, it happens. And typically what happens is that there is some sort of a second analysis that looks at people that didn't get the entire 2-dose regimen and only got a portion of it. They analyze those people in an additional dive in the data. There can also be, you know, you might decide that, you know what, I got kind of rotten side effects after the first one and I don't want to do that again. So I decline. I refuse to get the second dose. And that's allowed also. So the person still has their autonomy. They can still make a decision for themselves. We would hope that they, even if they didn't want to get that second shot, we would hope that they would stay in the study, because we can continue to follow them for safety over time. We can continue to learn more about how long someone's immune responses to the vaccine last, even if they didn't get that second dose. So we would encourage them to remain in the trial so that we can continue to monitor their safety and their well-being. But they do have the option to decline the second shot if that's their wish. And if they ultimately say, you know what, I want to drop out of the trial altogether, that's their right as well. And we, you know, we would honor that choice. How come Pfizer's not using warp speed? They felt that there was, you know, a layer of bureaucracy that they didn't want to deal with. And so they, you know, as a company they made the choice to do the trial themselves. And, you know, everybody's different. I can't begin to guess what their corporate environment is like and what informed their choices, but they felt that it was better to continue on their own. Raphael is asking about the rates of infection in the United States. Is there a number of infections that we anticipate in the study that would tell us whether the vaccine is effective? It's a great question. Most of the studies are going to wait until they get to 150 infections happening before they do an analysis that really says, do we see that the vaccine is working or not? Some of the studies have also plugged in some earlier double checks, like if there's 50 or if there's 100, because they want to have the independent data safety monitoring group look to see, is there any difference in where the infections are happening? Are they in the placebo group or are they in the vaccine group? You know, ordinarily you would think that if the infections are happening among people who get the placebo, that means the vaccine is working, right? So some of the studies have built in some earlier checkpoints, but they're not really getting to the place of saying, do we think that this vaccine really works, until they get to a minimum of 150 infections out of the 30,000 people being enrolled. So good question, Raphael. Thank you. I had not mentioned that at all. Maggie, your hypothesis is just as likely as anybody else's. We have absolutely no insight into the company or what guided their decision making. It could absolutely be a business decision. We just don't know. So I want to be careful that we don't start any rumors, but that is certainly one possibility. Let's see, Layla, do they explore different races responses? Yeah, oh, I'm so glad you asked this question. So we know that race is a social construct, right? But we do know that people of different races have different social impacts as a result of race. So things like poverty, things like living conditions, the kinds of jobs people have, the education people receive, the living environment where they may be in a more crowded home or a larger home with fewer people. All of these are things that are tied to different kinds of social constructs. And so we have to take all of these different things into account. So for example, we do know that, I'll use one really obvious example, African-American people are more prone to sickle cell anemia than people of other racial or ethnic groups. I have a cultural risk factor. I am descended from Jews of Eastern Europe, and my community is more susceptible to Tay-Sachs disease, which has a genetic link, right? So if a particular illness has a genetic association, then people who may be of the same race or ethnicity in your family's gene pool might have a different response. We do know that there can be some variation. We haven't yet seen an example where a vaccine is only licensed for one racial group and not another. That hasn't happened yet. Doesn't mean it couldn't happen. But it has not happened up until now. That's again part of why we want to be really mindful about enrolling a diverse cohort of people in our studies. We want to be sure that we're enrolling the groups of people that have been impacted by this epidemic. And because of all of these different social factors, all of the isms, if you will, we know that it is our racial and ethnic minority communities and our elders that seem to be most impacted. So having a really good representation from those groups in our studies means that we'll be able to get a clear answer. Does the vaccine work for Black people, for Latinx people, for Native American and other indigenous people, and so on, for our elders? The studies have been setting targets to try to enroll a particular percentage of people of the various groups. So that's something to think about as well. I mentioned this on Monday, and I got some positive feedback in the chat, so I'll say it again. We think about targets as numbers, right? We want to reach, a certain percentage of Black people enrolled, a certain percentage of older Americans enrolled, and so on. That's different from saying that we want to prioritize the communities that have been hardest hit, right? the people are very sensitive about the word targeted because it doesn't usually sound like a good thing when we say that a group of people is being targeted. In our culture, more often than not, being targeted is a bad thing. So we're going to leave the targets for our numbers, right? The target is the percentage of enrollment that we're trying to achieve. What we want to talk about is the way that we are prioritizing the groups of people that have been most impacted by this virus. And we want to make sure that they are enrolled and are part of answering the question so that we will know we've got a solid answer unequivocally that enough, Black people, Latinx people, so on and so on and so on, were enrolled, that we were able to answer the question of whether the vaccine works for that group of people, whatever group it might be. And the only way we can do that is to have, really a solid showing of from all of these different groups. It's a challenging message to deliver, right? We know that there is plenty of experience and plenty of unfortunate negative examples in the history of research that these same minority and ethnic groups have sometimes been victimized by unethical practices in the past. On a call the other day, I heard a terrific line from a Native American researcher who says that scientists failed us, but not science. The science has always been solid, but scientists may have applied that science in unethical ways. So we want to be able to help people separate, an unethical human being who did, some unethical research practice. That's not the same as science being unethical. We do have protections in place to try to make sure that those kinds of unethical practices don't occur anymore. All righty, I want to show one last slide of thank yous to the people that have helped to contribute to these presentations. We've had lots of physicians and researchers, folks at the NIH, different teams that have shared their graphics with us and so on, that we want to acknowledge their contributions. We still have about 5 minutes remaining. If there's any other questions that people have, again, you're welcome to unmute or put them in the chat, however you're more comfortable. A reminder again that we will be making the slides available to you and the recordings of the Zoom as well, if people want to go back and watch, or if there's members of your team that were not able to join, that you'll be able to share it with them. Or if you need to, just have a refresher in a couple months or anything like that, you'll be able to do that. You'll also be able to use the slides yourself. We want to encourage you. The slides have complete speaker notes. So if you think it would be helpful to use any of these slides and put them into a presentation that you're doing, you are welcome to do that. I see we're working on the distribution method now for the person. I'm not even going to try to pronounce that because there are too many consonants and not enough vowels, and I will get it wrong. So the person with the really complicated name in the chat, we are working on getting on the mechanism to get these out to you. You'll be hearing more from my teammate Jasmine, who will be sending it out. The other thing we want to mention is that if you wanted to take the slide and put it on a different slide template, like from your own organization, you're welcome to do that as well. We just ask that you acknowledge the CoVPN as the original author of the slides, but you're welcome to change and use your own branding and color scheme and those sorts of things. So thank you all. Thank you to those of you who are saying nice things in the chat. Thank you. I appreciate your kind words. We're here to help. Your clinic partners in the communities where you're located are here to help. One of the suggestions that we gave on Monday for the first batch of folks that participated was that you may want to ask the local clinic that you're partnered with to go through an informed consent process with you, do a little role play exercise and let someone from the SEAL partner team role play being a participant, and let one of the clinic staff go through a consent visit the way that they would with any other member of the public who was interested in joining a trial. And you'll get to experience, what's the kind of information that they share, how do they share information, how do they respond to questions. If you have the opportunity to go actually visit that clinic and see their space and know what it looks like on the inside, sometimes it's just a little scary because you don't know what to expect, right? So if you know what it looks like and you're able to help calm someone who's nervous, that would be a benefit. So we encourage you to work closely with your research partners and utilize everything that they can bring to you, just as they are going to utilize your expertise in reaching these priority populations. Jasmine just noted, you're welcome to share all of these materials broadly among your teams. We'll be getting the slides and the recordings out shortly. We wanted to make sure we did both presentations so that we could use the best recording in terms of the sound quality and so on. We'll be getting things out to you quite soon. Last chance. Any additional questions before we call it a day? Thank you for your patience and for sticking it out for a lot of information in 2.5 hours. I want to be sure to thank our interpreters who have made it possible for us to be working in Spanish and English at the same time. We appreciate your talents ever so much. To my bilingual teammates who helped translate questions for me, thank you so much. Alrighty, I'm not seeing any new questions in the chat. I'm not seeing anyone unmute. So have a good rest of your day. Wish you success in your efforts. And don't hesitate to reach out if we can help respond to questions that come up or anything that you might encounter. We appreciate all of you and all of your efforts. Thanks, everyone. Have a great rest of your day.